Hello students, it's Nazia Begum here, your physics lecturer, welcoming you all in today's lecture. So the topic for today is thermal expansion of solids. Okay, so let's see the definition first, then I will explain you. The phenomenon of increase in the size of a body due to heating, that is, increase in its temperature, is called thermal expansion. It is a consequence of change in the average separation between its constituent atoms or molecules. Different types of thermal expansions of solids are: first linear expansion, second superficial expansion, and third is volume or cubical expansion. So let me first tell you what is thermal expansion and what is cause of thermal expansion. So dear students, you all know that every particle is made up of so many molecules. All the molecules are arranged in a material in a proper manner. Okay, they all are having a proper separation between them. Okay, one molecule is at a sufficient distance from the other one. They all are having force of attraction between them and they are arranged in a proper manner inside a material. Now when we supply heat to any material, so because heat is a form of energy, so that energy is absorbed by the electrons, okay, or we can say molecules. Okay, whatever molecules are present there in a material, all that molecules absorb the energy. After absorbing the energy, they all get excited, okay, and they start vibrating. Now if more and more energy is supplied to them, so they leave their place and they start moving. Okay, in this course of their motion, they go away from each other. So whatever separation was there among them, now that separation increases, and because of increase in separation, they all go away from each other. And when the molecules are going away from each other, so obviously the size of the material will increase. So I hope you all have understood that how, because of heating, there is expansion in all the materials, all the solids. Okay, so this phenomena of increase in size of a body due to heating, that is in increase in its temperature, is called thermal expansion. So now three types of expansions are there. First one is linear expansion. So it refers to increase in linear dimension, that is length, breadth, height, etc. on heating a solid. So if suppose we are having a wire or something in which the length is prominent, feature. So that time what happen, when we supply heat to that material or that wire, so the length of that material will increase. That is called linear expansion. Now let L1 be the length of a solid rod at temperature T1 degree Celsius. On raising its temperature to T2 degree Celsius, let its length becomes L2. So here there is change in length. Okay, it is shown by this diagram very clearly. So here you can see one rod is there. Okay, initially at temperature T1, length of rod is from here to here. Okay, which is called L1. But as we supply heat to the rod, and when the temperature reaches to T2 degree, that time the length of the rod becomes L2. It expanded. Okay, and this much is the increase in length. So if we want to find out increase in length, so what we will do, final length minus initial length. So here you can see del L equals to L2 minus L1, and increase in temperature del T is T2 minus T1. Okay, study on thermal expansion reveals that whatever expansion is there, whatever increase is there in length, that is directly proportional to L1 and also to del T. Okay, L1 is the initial length of rod. So whatever initial length of the rod is having, del L, that is increase in length, is directly proportional to that. If initially the rod is having more length, so after supplying heat energy, the increase will be more. But if it is having less length, it will be less. Okay, if we are having a rod of same material, same cross sectional area, okay, all the properties are same but only the lengths are different. So we find that by increasing the temperature, the rod whose length is more increases more in length. Okay, and del L also is directly proportional to del T, that is increase in temperature, or we can say temperature difference. So whatever amount of heat we will supply, according to that only temperature difference will be there. So if we supply more heat, more increase in length will be there. Okay, so like that del L, that is increase in length, is directly proportional to del T also. So here we have del L directly proportional to L1 and del T. Okay, so here you can see proportionality sign is there. If we want to remove the proportionality sign and put the equal sign there, so we have to introduce one constant. So here you can see that constant alpha is there. Okay, so when we remove the proportionality sign, we can write this equation as del L equals to alpha L1 del T. Or in place of del L, we can put L2 minus L1. In place of del T, we can put T2 minus T1. So this equation take this form here in front of you. Okay, and here alpha is constant of proportionality and it is called coefficient of linear expansion. Okay, now from this formula, if we rearrange it, so we can get the formula for coefficient of linear expansion. Alpha equals to del L upon L1 del T, or L2 minus L1 upon L1 multiplied by T2 minus T1. Okay, this is the value of coefficient of linear expansion, and the unit is per Kelvin or per degree. Why unit is in Kelvin? Because del L is length, L1 also is length. So the unit of length and length will cancel each other and we will only have unit of temperature. And unit of temperature is either Kelvin or degree, and because it is in denominator, so it will be per Kelvin or per degree Celsius. Now from this definition, we can also define from this formula we can define coefficient of linear expansion. So here in front of you there is definition of coefficient of linear expansion, as it is defined as the increase in length per unit original length. Okay, del L upon L1. Del L is increase in length and L1 is the original length. So it is increase in length per unit original length per unit rise in the temperature of the solid. Or we can also say it is the fractional increase in length per degree rise in temperature. Okay, now again from equation 12.3, from this equation we get del L equals to alpha L1 del T. Okay, or we can also get L2 equals to L1 1 plus alpha T2 minus T1. How we get this one? So here you can see, here from this formula L2 minus L1 equals to alpha L1 T2 minus T1. If we transport L1 this side, so here it will be added there. Okay, so this equation will take this form. This equation will take form alpha L1 T2 minus T1 plus L1. Okay, then L1 is common in both the terms. Here we are having L1, here also we are having L1. If we take L1 as common, Okay, so what we will get here? Alpha T2 minus T1 plus 1. Okay, if we take L1 as common, so we get this equation, alpha T2 minus T1 plus 1, or we can also write it as 1 plus alpha T2 minus T1. Okay, so I hope you understood that how this equation came. L2 equals to L1, then in bracket 1 plus alpha T2 minus T1, and here will be the closing bracket. Okay, so from that equation we got value of L2, and this is L2 is the final length now. After absorbing the heat, this is the final length L2. Okay, now let's come to second type of expansion, that is superficial expansion. So as the name suggests, for linear expansion there was increase in length. For superficial expansion there will be increase in surface area. Okay, so superficial expansion refers to increase in surface area of a solid on heating. So here in this figure you can see one solid is there, and that bold line is showing the original size of the solid figure. Okay, this bold line is showing the original surface area, and after supplying the heat and increasing the temperature, okay, its size increases, the surface area increases, and here the dotted line is showing the increase in surface area. Okay, so let the original surface area of a solid be A1 at temperature T1 degrees centigrade. It increases to A2 on raising the temperature to T2 degrees Celsius. It is found that, again, as in case of length, it was directly proportional to the initial length and temperature difference. Similarly here, the increase in surface area will be directly proportional to the initial surface area and change in temperature. To remove the proportionality sign, we will introduce one constant, and for the superficial expansion, the constant here is beta. Okay, so this equation will take form as del A equals to beta A1 del T. In place of del A, which is change in surface area, we can put A2 minus A1. In place of del T, we can put T2 minus T1. Okay, here beta is called the coefficient of superficial expansion, and from equation 12.6, this one, we can find out formula for beta, which is del A upon A1 del T, or A2 minus A1 upon A1 into T2 minus T1. So here you have noticed that in place of alpha we are having beta, and in place of lengths we are having areas. Okay, rest all the things are similar to each other. All the steps, all the equations are similar. Okay, only the physical quantities have changed. So here we can define coefficient of superficial expansion as it is fractional increase in the surface per unit rise in the temperature. Okay, fractional increase in the surface per unit rise in the temperature. Again, on numerator and denominator area is there, so the units of area will cancel each other and only the unit of temperature will be left. So unit of superficial expansion is also per Kelvin or per degree centigrade. And as we have derived the value of L2, in the same manner from this equation, we will derive value of A2 here, which is the final surface area. Okay. Now let's move to third type, which is volume or cubical expansion. So as the name only suggests, in volume expansion what will be there? It refers to increase in volume of a solid on heating. So the whole volume of the solid will change now. So here again you can see one figure is there in front of you, in which the bold line is showing the original volume of one particular solid, okay, which is in shape of cubical shape here, but this solid can be of any other shape, okay. This is having cubical shape here, but if it is spherical, conical, cylindrical, any shape it is having, the same phenomena will be applied here, the same thing will be there, okay. So if by heating any material the volume changes, so that time it is called volume or volumetric expansion, okay. Let V1 be the original volume at temperature T1 degree Celsius. Let the volume of the cube becomes V2 on raising its temperature to T2 degree Celsius. So that time what happened? Again, by following the same steps, we will derive the formula for V2. So here you can see that increase in the volume del V is directly proportional to V1 del T, and if you have to remove the proportionality sign, we are introducing one constant here, which is gamma, okay. Here you can see gamma is introduced, rest all thing is same, okay. So this is your homework to derive the coefficient of volumetric expansion as well as the value of V2, okay. And when I'm explaining you any topic, so try to practice a derivation of that topic on the same day only, okay. By 2-3 times of your practice you will understand it in more clear manner, okay. So this is it for today's lecture. Tomorrow we will discuss the relation between alpha, beta and gamma. So see you tomorrow or in next lecture. Till then, goodbye, take care, do some productive work, and the most important thing, be healthy, be safe.